So it's lecture 4. And today, or in general this week, we're going to introduce sets and functions. So this is the content of sections 2.1 through 2.3. And many of you may already be familiar with sets and functions since after all you use them in calculus and other math. And so what we're going to do now is, what is different here is we're going to revisit these familiar concepts, but with much more precision, using this framework of proofs and propositional logic that we've developed. So the goal is to revisit familiar concepts with more precision. Through the lens of proofs. Of logic and proofs. And there are really two motivations for doing this. So one is that sets and functions form the basis for other more complicated mathematical structures that we're going to study. So these are the foundation for more complicated structures. And the other reason is that it's just a simple, test bed in which to try some proof techniques. Or for proof writing. So in today's lecture, I'm going to start by introducing sets. Then I'm going to talk about functions. We'll talk more about them next time. And then finally, I'll spend the last 10 minutes or so discussing a bit more about how to write proofs. So let's get started. Yeah. So let's start sets. So let me just state the definition. So a set is an unordered collection of objects. And the objects are called its elements. Okay, so another associated terminology is the set contains its elements. And we denote this relationship. So the key relationship is this notion of containment, right? So a set contains its elements. Sorry, should write this. Full. And this is denoted, X by the symbol, the sort of Greek small e, X, E, A. This means X is an element of A. And if I put a slash across it, it means X is not an element. Okay, so what's important about this? So let's look at a few examples actually before we do that. So here's an example of a set: 1, 2, 3, and then the number 1 is certainly an element of the set because it's contained in this collection. 4 is not an element of the set. And importantly, the order doesn't matter. The only thing that matters about a set is what are its elements. So this is the same set as if I change the order to like 1, 3, 2. I'll say a bit more about notation for specifying a set in a moment. And then there are some other, well-defined unordered collections of objects that we look at all the time. For example, Z is the set of all integers. Okay, and why is that a legitimate definition? Well, it's completely unambiguous, right? It's I can, in particular, if you give me any object, I can tell you whether or not it's an integer, right? So I can check whether something is an element of the set, and that's all that's needed for a set to be well defined.
I have a question. So what happens when a set has like a repeating element? For example, if it's like 1, 1, 2, 3, would that still be a set, or?
Yeah, so one question is A equals, let's say 1, 1, 2, 3, a set? And the answer is no. So a set doesn't have repeat elements. The only thing that matters in a set is what are its elements. So the answer is no, because a set is defined by its elements. So a set is just defined by which objects are its elements, not how many times. But this is another object, but this is called a multi-set. We won't be looking at these, right? We'll maybe look at these later in the course. So a set is defined by, this relationship of being an element, defined by the element it contains. So in particular, this set contains the elements 1, 2, and 3. And that's it. If you add another 1 here, it doesn't change that. So the convention is to not list repeats in a set. It's a great question. Okay, some other sets are the set of real numbers. Sometimes we use Z plus, the set of positive integers. And we'll see a few more as we go on. But roughly speaking, there are 2 ways to specify a set that we'll be using in this course. There are 2 ways to precisely specify a set. So one is what's called a roster notation. And here you simply list the elements of the set. So for example, the set A above, that's roster notation, right? Or, I don't know, I could, again, these objects don't even have to be numbers, right? I could, I don't know, I could list the set of, I don't know, things that I ate today, which, actually, what did I eat today? I guess granola, some sushi for lunch. Did I eat anything else? I don't know. I had some candy. Okay, but the set can be, it doesn't have to be numbers. But if you just list things, that's roster notation. Okay, that's nothing deep going on there. This obviously creates a problem if you have an infinite set, right? You can't list infinitely many things explicitly. And so the notation that we use more often when dealing with infinite sets is sometimes called set builder notation. And here, it's a way of defining a set given a propositional function. So given a propositional function, P of X, you can define a set to be the set of all objects which satisfy the propositional function. And the key thing here is this colon, which is read as such that. So what is this? This is the set. So this is the set of all x such that P of x is true. Or the collection. I guess I don't want to define set in terms of itself. Such that P of x. So using this, I can define some infinite sets very precisely. For example, I can consider the set E to be the set of all x such that x is even. So remember, even is something we defined in the last lecture. A positive integer is even. So just for concreteness, even x means x is an even positive integer. And so this is an infinite set. This is the set of all positive even integers. And I could be a little bit more explicit. I could say, well, this is the set of all integers such that x is even. And these two are the same definition, just here the domain is implicit. Right? So in principle, that x could be all kinds of other stuff. It could be real, it could be rational or whatever, but even only makes sense for integers, right? Or even for integers. And so I've excluded it there. So sometimes you don't explicitly state the domain, but both of these notations are valid. So you can have x in some set such that P of x. That's also set builder notation. Here are some other infinite sets. This is the set of integers such that, wait, did the color just change? Such that x is odd. Or here's the set P. This is the set of let's say positive integers such that x is prime. Okay. And these are all valid instances of set builder notation because x is prime is a propositional function, right? In this case, this is my P of x. So using this, you can define sets based on propositional functions. So any questions about this?
Kind of a question about roster notation. So for example, if we have a set of the integers 1 through 10, if we do like 1, 2, 3, ... 9, 10, is that like still roster notation, or can you not abbreviate?
Yeah, so that's a great question. So let's have the set C, which is 1, 2, 3, ... Did you say 10?
Yeah.
Yeah. So okay, this is kind of a gray area. I'd still call this roster notation because I'm not using a propositional function, right? I'm still listing it, okay. But I'm implicitly sort of, implicitly saying the pattern is obvious, right? Implicitly, there's an implicit pattern in this. And this, I would, people do this, but and okay, and when it's really obvious from the context, it's okay to do this, but generally it's more precise to list exactly. Although, by the way, if you wanted to do that, you could write that set in set builder notation. So how would you write that in set builder notation?
All x such that, well, all x in Z such that like 1 less than or equal to x less than or equal to 10.
Yeah. That's a perfectly valid way to write the same set. And okay, I should make a remark that, sometimes people so sometimes people specify an infinite set by listing the first few elements. For example, I could write E is 0, 2, 4, 6, 8, dot, 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 dot. And most people would say, okay, I'm looking for the even integers, right? But this is not completely precise. This is making an assumption. So this is okay. Later in math, people do this, but for now, I would say avoid this for now. Okay, so that's how you specify a set. And now let's talk about when are two sets equal, when is one set contained in another set, etc. Okay, somebody raised their hand. Yeah, please ask the question.
I'm wondering if you can use like a recurrence relation to specify a set, because it seems like it would allow you to conclude that things are in the set, but it would be difficult to show things weren't in the set. But I'm also...
So that's a great question. So we haven't introduced those yet. So just hold on to that for a couple of lectures. Yeah. And we will come to that. Yeah.
Awesome. Thank you.
Any other question?
Yeah. For roster notation, do all of the elements have to be of the same type?
So you're asking, do the elements have to be of the same type? No, in fact, we haven't defined type, right? So you could consider this set D, which is 55, math, I don't know, sushi, whatever, pi. You can put whatever you want. I mean, there's no constraint on the type as of now. It's just a collection of objects. The key is you should be able to tell whether something is an element of it or not. Okay. I guess I should make one interesting remark. Interesting remark is we have not defined what an object is. Okay. And as a result, what we're doing is actually called naive set theory. So naive set theory means you just go with a sort of intuitive definition of what an object is. And you don't really try to define it. Okay, so this is called naive set theory. And just to hint at what is wrong with this, there's something called Russell's paradox. Which is the following. Consider the following set. Consider the set A to be the set of all things X, so that X is not an element of X. Okay, so in set builder notation, that on the face of it looks like it makes sense, right? It's a set of all objects such that the object is not an element of itself. Okay, it's a little weird, but in principle, it could make sense. But now watch what happens. So now you ask the question, well, is A an element of A? Well, let's try to determine that. So case one is, okay, assume A is an element of A. But now what's the definition of A?
Well, if A is an element of A, then by definition, A is not an element of A.
Yeah. By the definition of A is not an element of A, which is a contradiction. What's the other case? Case two is that A is not an element of A. But then by the definition, A is an element of A, right? Which is also a contradiction. So that's bad, right? That means this is not a proposition because it's neither true nor false. Okay, so if you do some very crazy self-referential things like this, you can end up in problematic situations. And that's why there's this whole branch of math called axiomatic set theory, where you have to where you define which objects are legitimate. But we are not going to run into this sort of thing in this course. And we'll be dealing with very concrete objects. So the only thing to emphasize about sets is you can check when something is an element, and whether or not something is an element is a proposition. It's either true or false. Any comments or questions about that? So this was a big deal. Like, I think Russell, when he discovered this, he totally freaked out, and like people thought math, doesn't have foundations, and how can you know anything for sure and whatnot. But there is a way to avoid this. Anyway, so let's now talk about equality and containment of sets. So here are the definitions. A is equal to B if if they have exactly the same element, if they have the same elements. And formally, the way I would phrase this is, I'd say A is equal to B if and only if for every X is an element of A, if and only if X is an element of B. Right? So that means for every object, it's an element of A, if and only if it's an element of B. That's when they're the same set. And you kind of need this, right? Because you have these infinite sets. And how do you actually check if they're equal? So you need to have some well-specified way to determine that. So for example, the set of all positive integers, so such that X is odd, is equal to the set of all positive integers such that X is not even. This is because a positive integer is either even, if it's not even, it's odd, if and only if. Now, another relationship which comes up a lot is containment. So a set A is a subset of a set B if every element of A is an element of B. Now, formally, it's saying A is a subset of B. So this notation means is a subset of. That's how it's read. If and only if for every X is an element of A implies X is an element of B. So it's a one-directional arrow instead of a two-directional arrow. For example, the set of positive integers is a subset of the integers, right? If something is a positive integer, it's an integer. The set of integers is a subset of the real numbers. If something is an integer, it's real. But this is a one-way relationship, right? The set of real numbers is not a subset of the integers. So this slash symbol means it's not a subset of. Why is that?
Because if Z is a subset of R, it kind of implies that R is bigger than Z. And so how could you fit all of R
well,
into Z?
that's not quite right. So you said, well, if Z is a subset of R, that means R is bigger. Well, it doesn't mean R is strictly bigger. So because, for example, here's a remark. If A is a set, it's always a subset of itself. That's a tautology. So being a subset doesn't mean you're strictly bigger. And in fact, here's another important remark, or actually, yeah, go on. Somebody was saying something.
So then is the only way they can be two sets can be subsets of each other is if they're the same set?
Yeah, so that's a great point, which we'll be using a lot. A is equal to B if and only if A is a subset of B and B is a subset of A. But coming back to this example, why is R not a subset of Z? Why are the real numbers not a subset of the integers?
Well, there are many.
Because there exists.
Sorry, go ahead.
I was just going to say there exists an element of R such that it is not an element of Z, like 1/2.
Yeah, exactly. Yeah. So the reason is because the negation of this statement is true, right? There exists an X so that X is in R and X is not in Z. This is the negation of R as a subset of Z. And okay, for example, the number half, right? That's a real number, but it's not an integer. There are tons of such numbers. Okay, so that's the notion of being a subset. Any questions about this? Okay. Yeah, and it's, it's kind of a Venn diagram associated with this, that if you have a set A, then B is a subset of A means that B is sitting in here somewhere. Okay, I don't know. I mean, the Venn diagram is boring for this, but that's what it says. But B could be equal to A. Okay, and there's a special set here in this context called the empty set. Okay, so the set with no elements is called the empty set. Denoted with this phi, this Greek letter phi. So in roster notation, it's just like the collection which has nothing in it. And this empty set has a very special property. It's a subset of every set. So can somebody looking at the definition see why that's true?
Well, every element in the empty set is in every other set because this set has no elements. So technically,
yeah, exactly. Exactly. So the empty set doesn't have any elements. So it's true that for every X, if X is in the empty set, then it's an A because, well, it's never in the empty set. Right? So logically, the empty set has this property that for every X, X is not in the empty set. Okay, now one common point of confusion for people who are starting to work with sets is to confuse being a subset and being an element. So here's a remark. The remark is that subset of is not the same as element of. Okay, for example, the set 2, or okay, I mean, let's just say, like, the number 2 is an element of the set 1, 2, 3, but it's not a subset of the set 1, 2, 3. Because it's not even a set, actually. But, right, it's not the case that I mean, subset only applies to a pair of things that are sets. And similarly, this set containing the two element is a subset of 1, 2, 3, but it's not an element of 1, 2, 3. So the set containing the number 2 is not the same thing as the number 2, right? One of them is a number, the other one is a set. Yes, please ask the question.
If you said the set that contains 2, if you said that was A, and then A was part of a set, would then it be a subset and an element?
Yeah, okay. So yeah, so maybe your example is the set containing 2 an element of, maybe you meant this set.
Yeah.
Yeah, that's an element. It's in the collection. Yeah, so you can have a set that contains other sets as elements. In fact, that comes up a lot. And in fact, it comes up so often that it has a definition. So let me just introduce that definition. If A is a set, the power set of A is the set of all subsets of A. It's denoted with this curly P of A. So that's a set of all S such that S is a subset. So for example, the power set, well, okay, let's start off easy. What's the power set of the empty set? What are the subsets of the empty set?
Just the empty set?
Just the empty set. So it's a set containing the empty set. The power set of, let's say, the set 1, 2 is, okay, the empty set and all sets with one element, and then the whole set itself. And you can see that if you do this to a decently large set, you're going to get a huge set out of this. And here's a remark that we'll prove in general. The power set, so if a set has n elements, if A has n elements, the power set of A has 2 to the n elements. We will prove this later. And that kind of explains why it's called the power set, right? You raise 2 to the number of elements. Of course, this doesn't make sense if the set is infinite. Right, so maybe I'll add this definition. If A has n distinct elements for some integer n, we say it has cardinality n. And if it says cardinality n and is finite. And if a set's not finite, then it's infinite. And you can take a power set of an infinite set, right? You could look at the power set of the integers. That is some humongous set, right? It's a set of all subsets of the integers. Okay, so I've kind of just introduced, so far I've introduced, the notion of being a subset and of power set. So let's actually let's prove a little proposition about these new concepts of power set and being a subset. So let's call this proposition 1. Proposition 1 says that if 2 sets are equal, then their power sets are equal. Not very surprising. But let's prove it just so we're sure. Well, what strategy should we follow? This is a if A, then this is a if B, then Q statement. Which proof strategy would you like to try?
Probably direct.
Yeah, let's just try direct. So assume A equals B. Assume A and B are arbitrary sets and A equals B. So by the way, in this, there's an implicit quantifier here, right? In this expression, it's assumed that A and B are arbitrary sets. I guess we could be explicit about it for now, but often you will see statements like this where you say if A equals B, then from the context, it's clear that A and B are arbitrary sets. So, but really what we're proving is for any set A and B, if A equals B, then power set of A equals power set. Okay, so assume A equals B. And now we're going to use this remark on the previous slide, or maybe 2 slides ago, which is a very important remark for proving when that two sets are equal. 2 sets are equal if and only if each one is a subset of the other. So the way we're going to prove this.
A quick logistical question.
Yes.
Or conceptual question. What's the difference between an arbitrary object and some object?
Well, so an arbitrary object, so it depends on the context. So the word arbitrary is used to emphasize that you don't know anything about it other than it's an object of that type. Some can be used in both contexts, right? Sometimes it can be used, you can say let A be some set, although I don't encourage that. I encourage the use of the word arbitrary to make it clear that it corresponds to a for all quantifier. And I prefer to reserve the word some for existential quantifiers. Yeah, but any is like arbitrary. Okay, so assume A equals B. Now, what do we want to show? So we want to show that the power set of A is equal to the power set of B. Now to show 2 sets are equal, it's enough to show one is a subset of the other. So we will show P of A is contained in P of B, and P of B is contained in P of A. So this is important because I'm telling the reader and myself as the writer that the proof is going to be of this structure. I've broken it down into 2 subset inclusions. And so now let's prove the first one, right? So how am I going to prove that P of A is a subset of P of B? So by the way, there's a table here. And so far, what's on the table? Well, A and B are on the table. Okay, so for the first inclusion, so inclusion is just a sort of fancy word that's used very often. It just means one set is contained in another one. The first inclusion, how do I prove one set is contained in another set?
Show that each element in that set has to be another set.
Exactly. So, when you want to prove something and it has a definition, the definition tells you how to prove it, right? Because look what's written over here, right? A is contained in B if for every X is in A implies X is in B. So that tells us how to even prove that inclusion, right? So that for the first inclusion, assume S is an element of the power set of A. And now I need to show that, so now now power set of A is on the table, S is on the table. Now I want to show S is in the power set of B, right? Any thoughts on what property I'm going to use?
If S is in the power set of A, by definition of the power set, S is a subset of A.
Yeah, great.
Then since A equals B, S is a subset of B.
Okay, great. So by the definition of power set, S is a subset of A. And since A equals B, S is a subset of B. Now, we could belabor it and prove that just by digging in the definitions, but I'll skip that step. So since A equals B, S is a subset of B. And now what does that tell us?
It tells us that S is in the power set of B.
Yeah. So again, by the definition of power set, so by the definition of, let me just be very explicit. A power set of B, S is an element of the power set of B. And that's it, right? So now a bunch of stuff is floating around, B a power set of B. And now we have shown that the power set of A is contained in the power set of B because I assumed S is an arbitrary element of the power set of A. So I can just write as desired. So I showed the first inclusion. How would I show the second inclusion?
Kind of similar, but just like switching A with B.
Yeah. In fact, it would exactly be the same thing, but I switched the roles of A and B. Now, this happens a lot in proofs. And instead of copying everything down again, it's perfectly fine to write that. So the other inclusion is identical with the roles of A and B reversed.
And are we required to prove both because it's if and only if?
Well, it's not if and only if, right? It's if A equals B, then power set of A equals power set of B. So we have to prove both inclusions because I want to prove power set of A equals power set of B. Maybe that's what you're referring to, but yeah, you're right. In general, you have to do both. And in many cases, the two inclusions don't have the same proofs. And this one, we kind of just got lucky. Okay, so any questions about this proof? And again, maybe let me highlight the key logical steps, right? So this was because it's a conditional statement.
Professor, I don't think you can see what you're writing.
Oh, okay. Well, that's a shame. Okay, let's take this chance to have a 20-second break. I'll be back in 20 seconds.
Here comes our weekly technology little problems.
Yeah, it's really unfortunate.
I'm wondering, like, does this just happen with all programs as a thing? Because I know screen sharing can sometimes get a bit.
So this has never happened to me until this week, actually, until last week. But anyway, I'll be back in a moment. Any questions about the proof?
I had a question.
Yes.
Would this statement go the other way as well? Like, if
could we say
that if power set of A equals power set of B, then A equals B?
Great question. I'll come to that in a moment. So the question is the converse true? We'll examine that in a moment. Let me just highlight all the sort of logical connectives here. So I would say the logical structure of the proof is specified using words like this, right? So assume A equals B. It's a conditional statement. We will show is breaking up this set equality into two inclusions, this is showing another conditional that's necessary to show the first inclusion. Then I'm applying some definitions here. And then as desired is saying, I just finished showing the conclusion I wanted. And then, okay, I guess I'm showing the first inclusion and the second inclusion. So these are the keywords that sort of make it very clear what the logical structure of the proof is. But okay, now on to this interesting question. Is the converse true? So converse is the other implication, right? So let's call that proposition 2. If A and B are sets, or let's say, let me write it the same way, for any sets A and B, if power set of A equals power set of B, then A equals B. So by the way, curious, do people believe this true or false? We don't know yet, right?
True, probably.
Okay, so it is true. Let me write a proof of this. So again, now you have to assume something. So assume power set of A equals power set of B. Now again, we will show A is contained in B and B is contained in A. Now, I'm now going to show you a notation that's used throughout the mathematical world in this situation because it comes up so often. You just put a parenthesis saying this. This makes it clear that I'm showing the first inclusion. Instead of writing that whole sentence, we will show the first blah, 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 you just put this in. Okay, so now assume X is an element of A. So what's on the table? Well, power set of A is on the table, power set of B is on the table. I guess A and B are on the table, but now I have this element X, which is an element of A that's on the table. Now I need to show X is an element of B. Any thoughts on how to do that?
Maybe show that it belongs. You could show that it belongs to set of X, which is in the power set of A, which is in the power set of B, and is thus a subset of B.
Okay, yeah, I think I get what you're saying. So assume X is an A. So now observe. So observe is used to indicate that you're doing something or maybe a little bit thoughtful. Observe that the set containing X is now an element of the power set of A. That's because of the definition of power set of A, right? The set containing X is a subset of it. Or maybe I'll just add one more step. Observe that the set containing X is a subset of A. So it's an element of the power set of A. But now by the assumption, what can I say about this?
X is an element of the power set of B.
Yeah. So by the assumption, this set containing X is an element of the power set of B. And now by definition, the set containing X is a subset of the power set of B. So X is an element of B because whenever something is, that's what subset means, right? Whenever something is a subset of the set containing X, it's an element. Oh, sorry, this is B, not the power set of B. Yeah. So X is in B as desired. So I just showed A is a subset of B. The other inclusion in this case, okay, in this example, it's the same thing. You just replace the rows of so identical with A and B in place. I should say this is not usually what happens. Reversed. So actually, together we showed that A is equal to B if and only if the power set of A is equal to the power set of B. And the nice thing is, we know that this holds for any crazy set that we come up with, like infinite sets, whatever. So any questions about these proofs? Okay, so there are a few more operations on sets. I will tell you, I'll tell you 5 more operations on sets, and I'll just go through them quickly since I think you all already maybe know them. So, well, okay, I'll do sort of 3 operations on sets. The 3 most important ones, they correspond to the logical to and, or, and not. So the first one is union. And I'm not going to write the long English definitions. You can read them in the book. A union B, or I guess I've written as and or not. So let's start with intersection. A intersection B is a set of X, so that X is an element of A and X is an element of B. Maybe I'll, the second one is union. A union B is the set of objects so that X is an element of A or X is an element of B. And then there's complement. And this is with respect to a universe U. So U is a set containing all the elements that we're talking about. A bar is equal to the set of all X in U such that X is not an element of A. And okay, these are, I guess you've probably studied these in elementary school or high school. These have some very sort of clear Venn diagrams associated with them. So universe is just a big set that everything else we're talking about is a subset of. And so, there's a Venn diagram associated with each of these. So there's this like MasterCard kind of picture. If you have 2 sets A and B, then A intersection B is, I guess, this set in here. Here, so okay, this is called a Venn diagram. It's just a cartoon. The union is everything that's in A or B. And then the complement is, if this is A, the complement is everything outside A. Yeah, my coloring, especially with this, is not very great, but okay. So let's look at just a few mathematical examples of intersection, union, etc. Now, the point of this slide is that these operations on sets are clearly defined by logical operations and or not. And that's why, if you have 2 things that are sets and you take their intersection, that thing is also a set. There's an easy way to check when something is an element of the intersection. It just has to be an element of both A and B. So, I don't know, what examples should I do? I mean, okay, I don't know. What are some interesting examples here? Yeah, okay. I actually don't think it's worth spending time to do the type of examples I was thinking of. We'll see some interesting examples later. But any questions about these definitions? Okay, I'm not sure what happened here. Okay. I guess the one thing to point out is that this complement operation depends on the universe. If you make the universe, if you change the universe U, the complement can change. It's kind of seen from this picture. And then, okay, there's one more operation which is kind of related to these. I guess I said 3 operations, which is set difference. So A minus B is the set of elements in A that are not elements of B. So this is everything that's in here. Okay, so what I do want to point out is that there are now some simple but useful relations between these operations, which are nice exercises for writing proofs, some of which are on the homework. So here are some, these are called set identities. These are some relations between sets which always hold, regardless of what the sets are. So for example, I mean, there are a whole bunch of these, but one is that the complement of A union B is equal to the complement of A intersect the complement of B. And it's fairly straightforward, but I'll leave it as an exercise. Prove this. And now you know how to prove 2 sets are equal, right? Prove this using the 2 inclusion method that we did earlier. And then here's another one. A minus B is equal to A intersection complement of B. Let me see if I can find an interesting one to prove. Well, okay, I mean, there are other ones like the complement of A intersection B is A complement union the complement of B. So do these remind you of anything we've already seen in the course?
De Morgan's laws?
Yeah, so the first and last ones are almost immediate consequences of De Morgan's laws. And when you try to write down their proofs, you'll see that this is boiled down to an application of De Morgan. So these follow from De Morgan. Okay. There are a few maybe less obvious ones that are on the homework, like the power set of A union B is contained in the power set of A union the power set of B. But these are actually not equal. So these are, again, things you'll prove on the homework.
Wait, how's that? Sorry,
I got it backwards. Sorry. Yeah. Okay, so what I want to do now, I guess I should have said there's one more operation which comes up a lot, which is called Cartesian product. So the Cartesian product of 2 sets, definition, the Cartesian product of A and B is the set of ordered pairs A comma B such that A is an element of A and B is an element of B. So it's denoted by this times application. But it's times notation. A times B is a set of A comma B such that A is in A and B is in B. And ordered pairs means that A comma B is not the same as B comma A. So X comma Y is not the same thing as Y comma X. So the order matters, unlike in a set. And this contains many interesting examples that we look at all the time. So for example, Z cross Z is the set of all pairs of integers. Okay, ordered pairs of integers. But maybe something you've seen in a lot more detail is R cross R. So this, you know, if you took linear algebra, this is what we call R2. This is the set of all pairs of real numbers. These are just vectors with 2 entries. In general, you can look at Rn, which is just R Cartesian product itself n times. And this is a bit of a clunky construction, but you can see that this is just ordered tuples of n elements such that the ith element belongs to, I guess, the ith set here. But then you can use this notation to express all kinds of interesting, you know, other relationships as well. For example, I don't know, you could let P be the set of people in this class, and S be the list of, I don't know, songs on Spotify. And then you have P times S, which is a list of pairs of people and songs. And then you can define some interesting subsets of this set. This is the type of thing that, well, comes up, and if you're doing machine learning in some sense, you know, you could define the set W to be the set of all pairs in this Cartesian product such that P has listened to S, etc. So you can combine these operations to describe fairly interesting scenarios, right? Like Rn, you know, the situation with people and songs, et cetera, et cetera. Okay. So yeah, I realized the last few minutes of this lecture were fairly boring. Since this is mostly supposed to be a review, but does anybody have any questions about this notation?
Could you go back to the last slide for just a second, please?
This one?
Yeah.
Mm-hmm.
All right, thank you. Thank you.
Yep. Okay, so this is all I want to say about you know, sets and operations on them for now. What you really, you know, when you do the homework, you'll be asked to prove a bunch of set identities and just relationships between these different operations that always hold. And again, you know, the key advice I want to give you is when you want to prove something, the definitions tell you how the proof is going to go, right? Because they have certain quantifiers in them that is what, you know, that's sort of the clue as to how the proof has to be structured. Okay, so I want to say a little bit about functions. So functions are, again, something you're used to looking at in calculus, but let me now formally define it. So if A and B are sets, a function f from A to B.
I can't see if you're writing something. Oh, now I can. Never mind.
Oh, okay, sure. Mm-hmm. A function from A to B is a rule that assigns exactly one value, exactly one element, sorry, element of B to every element of A. And the assignment is denoted f of A equals B. Right. So for a particular element A and A and B and B. And the function is denoted or f is written as f maps A to B, where the set A is called the domain and set B is called the codomain. Now set A is the set of inputs of the function, and the set codomain is a set of possible outputs.
I've seen also like sometimes B is denoted as range. So what's the difference between range and codomain?
That's a great question. So there's a big difference actually. I will tell you about that in a moment. But the cartoon here is that you have two sets, which are just these circles A and B, and they each have some elements. And what a function has to assign exactly one element of B to every element of A. So for every element of A, there has to be an arrow that takes it to an element of B. And so let's say this is called A1, and this is called, let's say these are called B1, B2, B3, B4, B5. And this is A1 through A4. Then this relationship is that, f of A1 equals B2. And for every element in the domain, it has to get mapped to some element of the codomain. Now it's okay if an element in the codomain gets mapped to twice. There's nothing preventing that. And it's also okay if some element in the codomain is missed. So let me emphasize this. So this is a missed, again, it's in quotes because I'm not precisely defining it. Missed, this is a missed element of the codomain. That's okay. This is an element that was mapped to twice, right? So this element B2, this has a property that f of A1 equals f of A3 equals B2. Both of these things are perfectly fine. The thing that's the key thing is that everything in the domain is assigned exactly one element of the codomain. So just to emphasize what could go wrong and what would make something not a function is if you had a picture like this. You had A and B. And now for A1, there are two arrows. This is not a function. Okay, this is not a function because f of A1 is not defined in this case. So that's the definition of a function. It's a pretty straightforward thing. It's just a rule that takes an input and spits out an output. Now let me give some examples of functions. Well, here's a function from the integers to itself, defined by f of x equals x squared. Okay, so that is a rule that tells me for every integer in the domain how to produce a unique element of the codomain, namely the square. Here's another example. I could have the function g going from the real numbers to the non-negative real numbers. So this is a set. Maybe I'll just write the definition over here since we haven't done it before. So the set of non-negative real numbers is the set of x in R such that x is non-negative. And I can define this using the same formula by g of x equals x squared. These are different functions. The domain and codomain are part of the definition of the function. So these are not the same function. Here's another example. I could have h going from reals to reals by h of x is e to the x. So these are all things you're probably used to seeing in calculus. But then I could have some other functions. These can be any sets, right? For example, I could have now the function b going from a set A to its power set defined by the element A gets mapped to the set containing A. So actually there's one little caveat here. I need the set to be non-empty. I mean, if it's empty, it's vacuously a function, but that's not interesting. So we usually insist that it's non-empty. And so for any non-empty set A, I can define this function from the set to its power set. This is a valid thing, right? Given an element A of the set capital A, it outputs an element of the power set of A. Or I could express some fairly complicated relationship in this way. I could have the function m from the Cartesian product of the integers with itself to the integers defined by m of a comma b is the product a times b. So these are all legitimate examples of functions. The last two are maybe different from what you're used to seeing in calculus. I should say if you've taken Math 54, then linear transformations are an example of functions as well. Okay, so that's what a function is. And I'm in this rest of this lecture and in the course, we're going to emphasize two properties of functions. So any questions about this so far? Okay. So here are two important properties that a function can have. So the first one is function f from a to b is onto, also called surjective, if for every element of the codomain, there's some element of the domain such that f of a equals b. Okay, so the word onto is actually very, I think, well chosen and descriptive. It's saying that in this cartoon, if you draw a cartoon like this, there are no missed elements of the codomain. Every element of the codomain is equal to f of a for some a in the domain. So this is the formal logic specification of what onto function is. And going back to your question about range, there's a related concept called range. So the range, or let me just define an even more general concept. So if S is a subset of the domain, the image of S under F, denoted f of S is, or I'll just write is defined as f of S is the set of B in B such that there exists an A in S such that f of A equals B. Or equivalently, it's just a set of all elements f of A such that A is in S. And so the cartoon associated with this is you have A, you have B. Inside A, you have the set S. And now you have F that's associating an element of B to every element of A. And you could ask, well, if you just look at the stuff inside S, and you look at the arrows, so there are arrows everywhere, right? Because it's a function. If you just look at the stuff inside S, then S will get mapped to some subset of B, and that's f of S. So maybe a more suggestive picture is that this S is getting mapped to this other set in the codomain. The set in the domain S is getting mapped to a set f of S in the codomain. And there's this additional terminology of the range of F is usually just f of A. And it's important to remember that the image of S under F is a subset of B. So the most confusing thing about functions is people get confused about which elements are in the domain and which elements are in the codomain. But okay, let's now try to apply this. So that's the difference between the range and the codomain. The range doesn't have to equal the codomain. The range can be a strict subset of the codomain. So does that answer the question? So in this terminology that I've just introduced, so F is on to if the range of F equals B, or equivalently, if the image of A equals B. So now let's, excuse me?
Could you give an example where the range and the codomain are different? Like
yeah, so now we're going to go back to our examples and apply this concept. So now I'm going to ask for each of these functions, is it surjective? In fact, we'll just do surjective today. So now in this case, the domain is the integers. The codomain is also the integers. Now, surjective is asking, so if it's surjective, that, let's look at the definition. When in doubt, look at the definition. It says for every element of the codomain, there exists an element of the domain such that f of A equals B. So this is asking, is it true that for every, let's say, y in Z, there exists an x in Z such that f of x, which is just x squared, equals y. Is that true? Remember, this is the codomain, and this is the domain. So let's think about this, think about maybe thinking about this cartoon helps, right? So you have two copies of the integers, and you're asking, and now you have this map which is squaring integers, and it's really asking, do you get all the integers in the codomain when you do that?
No, because you're not going to get the negative integers.
Exactly. You're not going to get the negative integers, right? So if you look at this whole set here, it's just going to get mapped to a subset of the codomain, which is the positive integers. or let's say the non-negative ones. And so the answer is no, because the negation of this statement is true. So how would I prove that it's not the case? Well, I have to prove the negation, right? So the negation is that there exists a y and z such that for all x and z, x squared is not equal to y. And well, the proof of that is just consider, let's say y equals -1. So that was just the first example. Is this surjective? Let's look at the second example. So it's the same function, but the domain and codomain are different. So again, we're asking the same question. Is it true that for every y in the non-negative reals, there exists some x in the reals such that x squared equals y? Is that true? That's, yeah. This is now the second example.
Yes, right?
Why?
Because we can always take the square root of a positive versus, yeah, of a positive number.
Yeah, exactly. So the answer is, so this is yes. And what's the proof? So by the way, this thing was also a proof here, right? The proof is, well, assume y is a non-negative real number. What can we do with non-negative real numbers? We can take the square root, right? Let x equal square root of y. And now observe g of x equals y, right? Because if you square this, equals square root of y squared equals y. So g is surjective. Okay, so again, the definition of surjective, because it's so clearly logically specified, tells you how to prove or disprove whether or not something is surjective.
We say that if something is surjective, then the range equals the codomain.
Correct, yeah. So it says here, right? F is onto if and only if the range is equal to the codomain. So that's true, but writing that statement is maybe not as helpful for finding a proof, because it's kind of a very high level statement. It's more useful to write down the statement with the quantifiers because it'll tell you how to prove or disprove the statement. Okay, anyway, I'm sorry for going over time, but that's it. I'll continue talking about functions tomorrow. But any questions?
Can you quickly go to the other page that you were just writing on, like the example, that page for a second, please?